Great. I guess we get started. Hi, welcome everybody. Can you hear me okay? So this session is about lessons learned from building out hyperscale cloud services using Docker. So we basically probably know that Oracle is getting into the cloud business quite a bit now. And we're building out some internal services as well as external services. And this talk is about like an internal service that we may externalize, but we have some lessons learned there. We use a lot of modern technologies. And that's what this talk is about. So my name is Boris Scholl. I run the Microservices development organization in Oracle. I'm a recent hire, as so many of us. You've probably also heard that Oracle is like building out a new team there. So I came from Microsoft 6 months ago. And at Microsoft, I was working on Service Fabric and Container Service. So I've been in the microservices world for a long time. So the agenda, it's a pretty small crowd, and we can be very open and have like discussions. I think that's perfect. So the way I thought about it is I give you some objectives so that you know what you're getting out of that talk. And if you don't like it, you probably find another one. I'll give you a service use case because I'm talking about best practices, so it's good for you to understand the service use case, the architecture and everything, right? I'll also talk about the platform architecture as well as our design goals, what it basically takes to build out such a cloud service. And you can directly translate those type of learnings into when you guys are building out platform services on AWS, Oracle, or Azure. Right? Then I'll talk about a DevOps flow because it's fairly important when you work with containers, how we think about DevOps because we made some discoveries there. Then I'll hope I can give you a demo. I just tried it, but it's very slow so that you get a picture, and then I'll talk about all the lessons learned. Sounds okay? Cool. All right, so objectives, I already mentioned that. I just glanced over it. The difference from this talk to other talks is you get an insight into a real architecture. That's not a sample demo. That's not a sample app we build. That's really a service that's been used internally at Oracle. So what you get out of that is you probably get insight, you get insight into an actual real-world architecture as well as you get some ideas of where we struggled with in that game. So I hope that sounds good. So the service we had to build, as I mentioned, we had to build a service that's been consumed by other services, right? So think about we build out a database service, or think about we build out a compute service. Because those are distributed systems, we needed a consensus service for leader election, for configuration management, and so on. So that's really the use case. It's the service that I'm talking about is a backbone for other internal services that we built, and it offers leader election, service registry, configuration management. How many of you have heard about etcd? etcd? It's basically the brain of Kubernetes. That's what we're using there. So, and then what we may want to do at some point, because configuration management and that type of stuff is fairly important in a cloud world, we may externalize that service. That's not been decided yet. So right now it's an internal service, but we may make it available to customers as well. So the service design goals for us are, obviously it had to be hyperscale, right? And not just enterprise scale, because eventually we want to have a lot of customers on the Oracle Cloud. And they want to use our services. We have many internal services, many instances, so that thing really needs to scale, right? And it has to be absolutely highly available, because if that service goes down, think about if your brain goes down, your body doesn't function anymore, right? If that service goes down, a lot of our internal services go down. So it had to be resilient, because you cannot avoid failures. As you know, in distributed systems, they will occur. It's just going to happen, right? So it had to be really resilient. And then that's probably the most interesting part, from a architectural perspective, because it's an internal service, we wanted to run it as multi-tenant, right? We wanted to not have a service per box. We wanted to run it in an economically efficient way, right? So it has to be multi-tenant. We wanted to optimize hardware utilization and optimize cost, because after all, we're still Oracle, right? So we want to have very efficient services there. And we needed an agile delivery of individual services. So you see that service architecture I talk about are many individual components. And we needed to be able to, if, like, let's say the database team comes to us and say, hey, you need to update this, we wanted to be able to ship it right away. Right? So that led us to service design principles. And how many of you have heard about microservices I'm surprised. So we basically follow that pattern, right? And what it's really about is why we chose a microservices architecture is we had to optimize for time to market, right? It's less about decoupling, which is also a big portion of it, but we needed to be able to really ship those things and those components independently right away. So each service is delivered by an independent development team, which is also a characteristic of a microservice. We tried to automate everything because you all heard about microservices. You probably also learned that you should automate everything, the DevOps flow. And we automated pretty much everything all the way until we need to put it in production. That's a manual process. I'll talk about why and why we did that. But pretty much like automation of everything was one of the key things here. So the service itself consists of 9 separate services, meaning not service instances, just services, right? Like developed services, and they're delivered by 5 geographically separated development teams. So it's a true like microservice architecture with different teams on different stacks. What's really important there, and that was another design principle, and that's fairly important in a microservices world for every microservice application that we build. We had to adhere or we had to apply governance, right? Because if you think about it, we have all those different teams building out the services. If everybody's doing like tracing, logging on their own terms, you're gonna have chaos, right? So we decided, okay, we need to have governance in place, and governance starts with us, with unit testing. There has to be certain coding standards, code reviews on all commits, and then a common log format. It's very important in a microservices world that you basically agree on a common log format. So every service has to be deployable and testable. That means, because we also own Java, and there is this discussion, should we just ship a jar or war? We decided, no, it has to be a Docker container, right? That means every team has to put the stuff in a Docker container. And if it's not in a Docker container, it's not part of the pipeline. And then the last thing is it had to be built for operations, because operations is very important in a distributed system. So we basically build our custom UI dashboard that shows our entire CICD pipeline, that also shows our entire tracing and things like that. So from a technology stack, we've chosen the following things here. So we needed a reliable infrastructure, obviously. So we built it on our bare metal cloud services in Oracle. That's the new thing. As an orchestrator on top of that, we're currently using Mesos Marathon. The reason was because obviously we started building out that a while ago. So we decided to go with Mesos Marathon. We're gonna switch it over to our own container as a service or managed container service offering. And the reason is because right now our dev team, parts of our dev team need to operate it, and we just want to hand it, the operation of the cluster itself, we want to hand it over to another team, right? And then we are using Nginx, obviously for gateway stuff. Then technology is designed, I call it designed for operations. So Docker is obviously a given. That was very early on that we went with Docker. For diagnostics, we use the Elastic Stack, Elasticsearch, Logstash, Kibana. We also use Grafana for a better UI. And for time series database, we're using Prometheus. So to have like that time sequence database. On the Java side, we are using JaxRS, basically Jersey, Grizzly, Netty, and Coherence. How many of you have heard about Coherence? Okay, look, some. It's a detail. So, and then for the CI/CD pipeline, we're using Jenkins CI. As you can see, it's a very open, popular OSS stack. Right? So, from an architectural point of view, this is how it looks like. So we have on the right-hand side, we have what's called the operator. So the operator is a guy who basically sets up a new cluster, a new etcd cluster, right? Think about it, I said configuration management leader election, that's etcd. So if we need a new cluster, that's done through the operator. Or there's a new version, we basically go through the operator and says, hey, upgrade from etcd version 2 to version 3, okay? So that goes for a load balancer. That's what we call the operator load balancer. That's also Nginx. Then we have a bunch of management APIs. And then we have a thing that's called service orchestrator. It's a little bit confusing. Don't get, like, it's not an orchestration of containers like what Marathon does. It's really, I'll talk about more what that component does. It's more like our own orchestration for spinning up our application. And then it basically has the etcd gateways, and then it's backed up by coherence. So think about, we provide etcd APIs, and the data is stored in coherence, which is basically an in-memory data grid. So it's highly available, highly reliable. So as I mentioned, we wanted to have it multi-tenant available. The way we basically build or implemented multi-tenancy there is we're okay with having the data in the same cluster. It is more about the network separation on our end. So we have, on the left-hand side, those are like the tenant networks. We have load balancers, which we call tenant load balancers, which are Nginx. And they're basically, think about it as being a wormhole from our service network, right? Service private network on the right-hand side into the tenant networks, right? So that they can basically make a request into the service. That's what those load balancers are. Platform components, again, I already mentioned it. We use Nginx. We're not using Nginx Plus, so it's literally the open source version of Nginx. For control plane, load balancer, and the tenant load balancer. Control plane is the operator one. And as I mentioned, the tenant load balancer is basically that wormhole thing. The management APIs that I showed you, they're basically just the endpoints, what management APIs do for the console, the web console, as well for the CLI that you can use against it. And then the etcd service itself is really, as I mentioned, a virtual concept, because you can go and install etcd as is, right? And it's basically storing the data itself, but we took basically etcd, like the head of etcd, the APIs and everything, and put another backend underneath it, right? And that's what we call an etcd cluster. So the etcd gateway are, in the coherence world, the front-end nodes. The storage-enabled nodes are the back-end nodes. And the data is basically persisted to our VMs. So I talked about that weird thing that Orchestrator, right, not Marathon. Why did we have to do this? It's actually quite interesting, because when I joined the team, we were starting, and we did a little bit on the architecture, and I said, why do we need another orchestrator? So it's basically a bridge. Think about, we're building out a service with a bunch of components that depend on each other, right? So, and we need to be highly available, as I mentioned before. We cannot just take down components. We need to make sure we can take them down, or we need to make sure that they're basically being spun up in a certain order, right? It's more like, hey, our entire application are those 9 services that I mentioned before, right? And they have a certain order. They need to be started, right? A lot of orchestrators do that nowadays, but we also needed to have a certain order when we updated it. We needed to make sure we get a response from like coherence, say, hey, your data is safe, your data has been replicated, and things like that. And then the other cool part is it supports target environment profiles. Because think about CICD, right? We say we have our definition of our microservices application in those 9 services. And we say, okay, I want to spin up that environment on a laptop. I want to spin it up in the cloud. I want to spin it up in like our production environment. What that also has to do, or what that also does is, you know, if you have different environments, they have different resources, right? So if you have just a test environment, you don't want to have like 5 nodes. You probably just want to have 2. So what the orchestrator also does is it provides environment profiles, where we actually adjust the cluster size for etcd based on the environment we deploy it to. It also adjusts the JVM resource usage, right? Because if I deploy it on a laptop has less memory typically than our bare metal machines, right? Then we just use the orchestrator, deploy the application, and say, hey, it runs in a dev environment, and then it adjusts, for example, the Java settings and things like that. So that's why we need that awkward thing in the middle there. The platform manifest is basically what I already touched on, is the collection of components. There are all of our Docker images listed in there, pointing to the registry along with the versions. And that basically gives us the final state of the application. And the platform installer is that thing that actually installs it into the environment. So that's at a high level the architecture. Does that make sense, or is that super confusing? Kinda, sort of? All right. So from a runtime architecture, the way it looks like is very simple. You have tenant. Think about a client. It can be a service or a program, right? That needs to put some data into the etcd store. It runs in a tenant network, and then it goes through the load balancer service, which is Nginx, as I mentioned before, and then it basically gets routed to an etcd gateway, and that routes it to a backend that is available. Obviously, for high availability, all the instances are spread across availability domains, so if one availability domain goes down, you still be able to access your data, and you still have your leader election there. So that's it on the runtime side. So that was the architecture overview. Give you a little bit of testing strategy, what we're doing, before we get into the best practices. So testing strategy, as you know, you have, in a microservices world, each service is owned by a service team, and they're typically responsible for the entire pipeline, right? They're like empowered to make an update and put it into production. So we have that too. So we have service level tests. They're owned by each service team. That includes the unit tests, component tests, and integration tests. And they run, let's say, a developer in prod basically updates the code, checks it in, it runs as part of the individual build in the CICD pipeline. Then we have what's called platform level test. That doesn't mean there is a team that pushes a button, right? It's still up to the individual team. What the platform level tests do, they're basically like looking at the bigger picture. They're owned by a central test team. That doesn't mean it's not automated, right? It's just a different team that says, okay, those are the tests that make sense for us to deliver. That's what we need to have in order to ensure that our components are actually safe. And they include end-to-end tests like functional acceptance tests, minimal acceptance tests. It's basically like tests against etcd APIs, upgrade tests, right? And things like that. Longevity tests, as soon as we have a build candidate for one service, we basically run along probably like a day of tests against it and see if something happens, like memory leaks and things like that. Upgrade tests, so if we upgrade one component to make sure the entire application still works. And then we have, of course, performance and stress sense tests. And then we do something very special, which is Chapson testing. I don't know, you guys are familiar with Chapson testing? So it's, because we're dealing with a distributed system, we need to make sure that the data is always consistent, right? So if you write to a node and then actually coherence replicates it to another node, as you've seen in the architectural diagram, and something happens, there needs to be tests in place that on a cluster level, your data is consistent always, right? As well as for the end user. And there is a testing methodology, it's called Chapson testing, and that's part of our pipeline. It's actually quite interesting. If you guys build distributed systems with like distributed data, that's actually a test you want to look at. And that's part of our automation flow there. So from a CI/CD pipeline, the way it works is, the first step is what we call verification. So we use localhost installation. Localhost doesn't mean it runs on your laptop. It can be on a virtual machine. It can be in our cloud. It just means like it's just a single host. And we do that with the last published manifest. That means it has, think about the manifest I talked about, it has all the components in there, and your new one, and we just deployed. We deploy the entire stack, right, for testing there with all the components. Then we run functional acceptance test in 10-minute parallel chunks. So because one thing, and I'll talk about that in the lessons learned, is if you have a lot of teams that commit a lot of stuff, right, your end-to-end testing actually becomes fairly long, right? So we needed to find a way that our developers get a response back in a timely manner that says, hey, my component was tested successful, I can move on, or we've discovered it. So we broke down the tests in parallel testing. So we basically, all the tests that I talked about are broken up in chunks, each 10 minutes, and then we run them in parallel on different hosts. And then we run the upgrade acceptance test, again, from one component to another. Like, think about, you have Nginx gateway version 1 to version 1.1. So the next one is the pre-stage is a production-like environment with the last published platform manifest again. But this is like not on my local machine. It's really production, it's pre-stage, right? Deploy a platform instance from scratch, as I mentioned, with a new component. So everything is going to be wiped out and deployed from new. Then we run all the acceptance tests and the upgrade tests and see if that's okay. So after that, we go into staging. And as you can see, that's a very traditional like testing pipeline, right? But it's very agile because it's all automated. There is no human interaction at that point. I should point that out. That's all automated. So and then we are in the staging environment. And that's a production-like environment, which is mirrors our bare metal cloud. And then we upgrade to the new version. We run a bunch of tests. And if that tests were successful, we take the manifest that we just created. Now we have an updated component in there, and that's going to be our new manifest, right? And then if another team basically starts over, that's the line they go. And then we have the production candidate. So the production candidate, and as I mentioned before, we try to automate everything, and we actually couldn't. We couldn't do continuous deployment, right? And the reason is, we're running stress tests, we're running Jepsen tests. We get so much data, we haven't found a good way to automate the interpretation of that data, right? So we still need a human person who looks at that and says, yes, that actually works, we don't have any problems, right? So that's what we haven't been able to automate. And that's mainly because, again, there's a lot of data coming in from stress testing and Jepsen testing. And so we produce a production candidate every night with all the tests, and we say, yeah, like based on what we've seen, it looks okay, but then we still have a person that actually looks at it and says, yes, that's actually something we put in production. That being said, we are actually working on trying to automate it, but we haven't found a good way yet. So there is a team right now who's actually trying to do this, because eventually we want to get into the continuous deployment, right? Promote it in component or service all the way through it and deploy it and call it a day. But that step is actually holding us back. Another interesting aspect here probably is to mention, once we have that production candidate declared, and someone says it's okay, we have a production release pipeline then, where it basically goes through again. It's a smaller one. But so this is it. I think from a architectural perspective, you get an idea how we build it. You get an idea how we do that DevOps, right? So let's try if I can actually show it to you. Oh, cool! It works. So this is the Marathon UI. I mean, you guys are familiar with Mesos Marathon? Okay, so that's a Marathon UI. It's basically like the orchestrator that takes the containers and schedules them in the cluster. That's the thing that I mentioned that we'll be replacing eventually. But from an end user perspective, it looks more like this. So this is the website to create a new etcd store for your service. As you can see, that's why I said we haven't decided whether we make it publicly available. It's more like an internal UI yet, right? But it says, okay, I don't have a store yet. And what I can do in here, I can create a new store and give it a name. Call it demo store. I can choose the version. I have my network. Think about that's the network of that's my network of my tenant, where I want to create that instance, right? And then I can have some automatic backups and stuff like that. That's for the data. And then I just create the store. And so now it's creating it. If I switch over to Marathon, it's going to create a new application in Marathon. As you can see here, it says tenant 1. And in tenant 1, that's actually, think back to the architectural diagram. Now you have those etcd 1, etcd 2. That's actually the application now, okay? And the cluster itself runs here in the service VCN. And let's see if I can make that bigger. So in the service VCN, you see all those components that I mentioned before, right? You have the etcd gateway, you have the etcd storage, the orchestrator, and the diagnostic stuff. That's the part on the right-hand side of the architectural diagram that I was talking about. So if I go back here to applications, go to tenant. This is my VCN1, and then I basically have my etcd store. Now a service team could go in there, grab the endpoints for that particular etcd instance, write the data to it, use it for leader action, and so on and so forth. Then we have the other UIs. So that was the UI for a tenant to create it. The other UI we have is for an operator. And the operator actually just shows you how many clusters we have running right now. We currently have one etcd cluster running. So that means like one backend. But an operator could go in there and say, we need a new cluster, and go in here and create a new cluster, manage the cluster, or upgrade it to a new version. Let's say there's a new etcd version, which is actually true, like from etcd 2 version 2 to etcd version 3, they can just go in there, upgrade it, and your application wouldn't be impacted at all, okay? Cool, so as you can see, it's a fairly complex architecture, right? It's not a lot of services, if you will, like there are microservice applications with thousands of services, right? But it's a fairly sophisticated architecture, given the nature of the use case of the service. So what are the lessons learned here? Let me switch back here and go. All right, and go to the lessons learned. So the first one, as I mentioned before, it's a lesson we've learned, but it's also a best practice for any distributed system. Right? You need to assume that your services fail, right? That's not something that may not happen, that's gonna happen, right? So what you need to do here in your code, you actually need to implement like certain things. And there are things we are using, obviously, retries, right? So once the service endpoint cannot be reached, we're not saying it's down, we just retry it. What's important there is that those operations need to be idempotent. So to give you an idea, let's say you make a call to a service, right, which puts a message in a queue, right? So, and that thing fails, and you implement a retry, and you put a new message in there with the same value, right? So you have that message twice in your queue, right? What you need to do is you need to make it idempotent. That means you give it like an ID, right, where you check, hey, has this been processed or so? That's very important there. Then we are using circuit breakers, which is basically at some point we give up retrying. Right? We just know that thing's gonna fail, and we need to snap out of it, if you will. And that's where we use circuit breakers. And in our case, they're combined with a retry pattern. And then we're also using bulkheads, which is basically trying to avoid that exhaustion of threads and things like that. The cool thing here is, except the retries, like the bulkheads and the circuit breakers, are actually available for Java developers in an API. It's called Hystrix by Netflix. So if you go to Hystrix or Netflix OSS, there's a Hystrix library, which you can just put in there, and it's really great. It comes with a dashboard. So the other thing is lessons learned, and that's true, is now think about in a microservices world. A lot of people say, hey, that's great, and I have so many services, right, and they talk to each other. What a lot of people completely underestimate is there's a lot of chattiness going on, right? So, and that actually can become your bottleneck. So what you need to do there is you need to have you need to think about what kind of protocols you want to use, right? So, and in like a microservices world, you need to think about, is this an external service or is this an internal service? Because for an internal service, you can use different protocols that are probably better for performance, right? So in our case, we are using like for the etcd itself, we're using HTTP2 right now because that's what's required for etcd v3. But internally then, we're using TCP UDP as well because it's just faster. And for the coherence connection, they have their own protocol there. The other aspect is, like, because you're in a microservices world, like in ours, you're exchanging data, right? And the data needs to be serialized and deserialized. And that can actually become your bottleneck, right? It may not happen if you just have like 10 instances, because that might be okay. But if your application grows, and think about, we built the service to be hyper-scale, right? then it can actually become a bottleneck, right? And you need to figure out what's a good way of serialization, deserialization, right? The thing is, we, as I mentioned, we're using Chetty for that type of stuff. That does it for us. But there's also one thing you can do is you can actually, maybe you don't need to serialize it again, right? Maybe you can just pass it on and just augment the data and things like that. So that's another lesson learned. That's really something that's very underestimated in the space of microservices there. Then Docker and Java apps. What a lot of people know is that Docker is awesome, right? And you can say, hey, I just want you to use that amount of memory. I just want you to use that amount of CPU, right? Problem is your JVM doesn't really care, and not a lot of people know that. Right? And so we also figured it out. We own Java, right? And so it doesn't honor the Docker runtime metrics that you set there. So what's happening there is what we figured out, the Docker daemon kills the container when it's crossing the constraints. So what we've done is we actually specify the max heap size for the process, and I'll show you how we do it. So basically, every time we start up a Docker container with a JVM in there, we tell it the JVM inside. You tell you can use that much memory, can use that much CPU. So the other thing is, now you're dealing with a Docker container, right? But you also have, like in our case, Mesos Marathon, you have a deployment JSON file. You also need to make sure that that deployment JSON file is somehow aware of what's going on there, right? So it's a tricky part. The good news is, on the memory part, that's addressed in Java 9. So the memory thing is going to be addressed. It's going to go away. You don't need to worry about that anymore. You still have to worry about that in the CPU case, and it's pretty much the same issue, right? If you want to restrict it, you actually need to adjust the JVM settings to what you do. So the other problem is if you're not doing that, as I mentioned before, your orchestrator shuts it down, your Docker shuts it down, so your application may not work properly. So the way we're doing this is, on the left-hand side, we basically have a Docker file. Like that's just an example of Docker file. It's not the full Docker file. And we're going to launch a startup script in there, right? Start.sh. Every time the Docker container comes up, we execute that script. Then there's a marathon JSON file. How many of you know like a marathon JSON file? No. So think about it like Docker files you guys know, right? I assume. So in a marathon JSON file, think about it as your description of an application. JSON file that says, hey, use that container, set those environment variables, right? Use that much CPU, use that much memory, and that type of stuff. Think about it as a description of your application. I can actually show you one. Because going back here, going back to Marathon, let's grab, going back to applications, go to the service VCN, and which one should I pick? Let's take the storage one, go in here. So if I look at the configuration, this is basically the JSON file, right? So you define it, you declare the JSON file, you submit it to Marathon, and Marathon grabs it and then basically schedules your container on your cluster. And that's how it looks like, right? And it says container type Docker. Then it says where to get the Docker image from, right? Which networking to use, the container ports, service ports, and so on and so forth. So this is the idea of the JSON file. So what we had to do here is, obviously, going back to this one, in the marathon.json file that I was just showing you, we had to define environment variables, right? And we're saying, okay, the max container CPU quota you can use is 1, and here the max container memory quota is 4 gigs, right? It's your JVM max size. And then that's the environment variable. And that's when I mentioned you need to sync it with the orchestrator as well, right? Because then you also need to tell Marathon itself how much memory it will adjust or give it to that container, right? And how much memory in that case. So that's the container memory that Marathon will give to that container, right? And that's what we set it to, the Java VM inside the container. And we have a factor of 2 in there. And that's how we figured it out. There's actually not a formula. I cannot give you a formula and say you should do this. Java 9, it's gone anyways, but there is really no formula. We figured for us it works best if we have a factor of 2 in there, right? So then once the container starts up, we have a container image which basically has Oracle Linux in there, based on Oracle Linux, the coherence component. And then we have that, we basically execute that start.sh script, which is basically a command, an instruction in the Docker file. And that looks exactly like that. I actually copied it from our source code. And we say, hey, you know what? Get the memory quota, get the CPU quota, right, from the environment variable, and adjust it to the JVM. So, key takeaway here is Java 9, memory, you don't need to worry about it anymore. JVM will honor it. If you do things with the CPU and things like that, you still need to do this, right? And we're currently looking at Java 10 because it's not super easy to implement that, to be honest. All right. So the other thing is lessons learned, Marathon, or some other orchestrators. Because the interesting part is, what we figured, especially in the case of Marathon, it gives you a container state, right? So your container is ready and running. So you get a green light and awesome. It doesn't mean your service inside the container is ready. And remember, we have that problem. You need to make sure that certain components are up and running. Right? So what we had to do is we had health check URLs where we actually ping the service and say, hey, are you there? Are you there? Are you there? So we couldn't rely on basically the status that Marathon gives us, right? And that's in general a good practice there. It's very interesting because I've been, as I mentioned before, I've been dealing with that stuff for quite a while, especially on Azure with container service. Never really thought about it too much, if I'm completely honest, until I came to Oracle where we had the requirement that that service has to be up and running. Yeah, well, that does it. That's totally, no, it doesn't work. So very interesting. So I thought I'd put that in the slides. Nginx. So dynamic reconfiguration. I honestly don't know if Nginx does that, but Nginx, the open source version, doesn't do it, right? So when we need to reconfigure Nginx is, think about I have the tenant load balancers that I had in my architecture library. Now I set up a new cluster, right? I have new etcd gateways, I have a new cluster. How do my tenant load balancers know about that? So what we do is actually, our orchestrator takes care of it and says, hey, I have a new cluster, that's the cluster endpoints, but we need to update the Nginx configuration URL while that thing is running, right? So also not easy, you don't know, it's very easy, and I have an animated slide on that, how it works. But we didn't know if that change was applied because it was very unreliable telling us, yeah, Nginx process is running, but has it the new configuration or not? Right? So we do the same thing. We do basically, we recycle the Nginx process and then we ping it and say, hey, you're back up. We also disabled Nginx logging because again, we have our own stuff, and then increase the worker processes to match the load because they're quite under some load. So the way it works is, and this is a nicely animated slide. So on the right-hand side, it's a simplified diagram of what I've showed you before. Right? And so Orchestrator is there. That's the thing, again, that creates a new cluster and things like that. So comes in, I want to add a new cluster, and operator adds a new cluster. New cluster gets added to the bare metal cloud service. Then the cluster starts operating. And then what's happening then is it basically reports back to the orchestrator, says, hey, I have a new cluster, I have new etcd gateways for you, right? Then the orchestrator takes the new endpoints and issues and puts it together and actually sends it to Nginx. So our Nginx image is not just an Nginx image, it has a Java component in there that offers an endpoint where the orchestrator can send an information to, right? And that's the yellow thing. I should have probably said thing there. So the Java component receives the new routes for Nginx, adds it to the Nginx configuration, recycles the whole thing, will ping it, say, hey, are you back up? And once it's back up, it can actually use, a new tenant can use the new cluster. Right? So I hope that slide kind of illustrates why we had to do this, because we create and remove clusters. So from the tenant side, we needed to do that dynamic configuration. Containers, it's actually, I think, meanwhile, it's common sense to image or to version your container images, because we found, if you don't do this, I don't know if this is still the case, but it basically applies the latest tag, and that doesn't necessarily mean that's your latest update, right? It's basically your latest on-version thing. So you should always do the container image versioning. Use small base images. It's also one thing that's not something that's obvious right away, because a lot of examples are built on, let's say, big images like Ubuntu, and there's nothing wrong with it. But if you need to start instances fast, right, you want to make sure that your container image size is pretty small. Because if you're in an orchestrator, and let's say you're scaling out, right, and it says, hey, I need to launch a bunch of instances on node 3. That image is not on node 3 yet, right? So it needs to pull it down. If you have a large image size, it takes a while to pull it down. It's nothing to do with the container launch time. That's super fast. The pull is what's taking time, and that's taking time for your service to come up. So think about keeping the sizes small. What we've also done is, for Nginx, we actually use one base image for multiple purposes. And I don't know if that's a best practice or not. I just added there because you may run into that situation. So Nginx, the way we're using it, doesn't support HTTP2 right now, right? So we had to add code to support HTTP2. So we updated it. But our operator, load balancer, also on Nginx, doesn't need HTTP2 right now. We haven't moved it over. It's just an HTTP. The tenant load balancer, though, needs it because etcd version 3 needs HTTP2, right? So what we're doing is we're actually just passing a flag in and say, we have one image for both use cases, and we just pass a flag in and say, okay, is it a tenant load balancer or is it an operator load balancer? And based on that, we enable it or not. So finally, the CICD lessons learned. Automation everything may not be possible. Again, as I mentioned before, we desire or we try to achieve that goal, but we cannot right now. This is less a technical thing. It's more like if you deal with various development teams, which you do in a microservices world, let the development teams choose what they want to use. Right? So we have a whole mix, because as you probably know, Oracle is acquiring a bunch of companies, right? That's what Oracle does. And we have a bunch of companies and a bunch of acquired companies. They use their technologies. They have their own tools. They may use Gradle, not Maven, and things like that. So we said, you know what? You guys, you use what you're really comfortable with. So in that case, we have supporting both Maven and Gradle projects. That also helps you from an organizational perspective to get your devs way more involved in the CI/CD pipeline. Because before, they don't really care, right? Especially if you force them to use certain tools, certain frameworks. In that case, we can see in our development teams, they're way more involved. They have way more opinions in how this whole thing should be automated. Then we're restricting the testing pipeline to deployable components. I mentioned that before. Our deployment component or unit of deployment is a Docker container, period. We have teams that just produce a jar, but they are required to put those things in a Docker container. Right? Kind of like common sense, right? Because our entire pipeline and everything is built around that. And then the other thing is dev projects should be responsible for managing dependencies with other projects. So we basically push that requirement down to the dev teams. It's working fairly well. Then every dev team member should be able to stand up an environment, an isolated environment in a very easy way. And that's why we created, remember that Orchestrator thing that I talked about with environment profiles? It's very easy for a developer now to reproduce something in our case because they just basically say, okay, I have a deployment profile development and it spins it up on a virtual machine in the cloud. And then they can test it and they basically have the entire environment running there. The other part is the Agile testing pyramid of unit integration and end-to-end tests, right? So what's taking the longest? It's your end-to-end tests, right? If you think about it. And if you go through the entire pipeline all the time, it's a lot of time. And developers want to get the response back. So we actually emphasize more on the unit testing, more on the integration testing right at the beginning, right? And that's why we call it like the pyramid, because our testing is, we do less end-to-end testing, we do more emphasis on unit testing and things like that. Parallelized testing where possible to cut down the time. That's what we've done. Before, our tests were running for quite some time, and then we cut it down into 10 minutes chunks, as I mentioned before, by spinning up those tests in parallel. It's good because developers get the feedback right away. Then the upgrades, as you've seen in my slides, we test upgrades pretty much like from the beginning, right? As soon as we, as a team, has produced a new version service, we test the upgrade of the service with the entire application. So we do that very early in the cycle, and that's been proven to be very time efficient. Because think about, guys, what we really want to be able to do is we want to be able to react to new requirements quickly, and we want to be able to push it out, right? And so time's of the essence. We don't want to go all the way and then just like after 3 hours of testing and potentially longevity test, figure out the upgrade doesn't work. So we do that very early. And then the intermittent failures in end-to-end testing be addressed right away. Do this as well. Then developer-focused dashboard to essentially identify failures in the pipeline and blockages. So as I mentioned, our CI/CD flow, our CI/CD system is Jenkins, and we write all the Jenkins output to a special database. And then we have our own homebrew dashboard on top of it that actually shows which component is at what stage, which component is using what manifest. So every developer can go there and see if his check-in is actually going through the stages or not, right? And they can also see which other components are part of that testing. So it's very, very important. Then the diagnostics piece, as I mentioned before, I front-loaded that actually because diagnostics is key. In a distributed system, diagnostics is key, even in the testing. And we are using a common log format. I mentioned this before. It's very important. Even like think about date, time formats, right? One team puts it in a certain format, another team puts it in a certain format. You want to order it and things like that. So diagnostics is really key. And again, as I mentioned before, we're not just using Elastic for logging. We're also using Prometheus. So we're using. You may argue that we're using too many systems for diagnostics because you also need to operate those systems, right? But it's really proven valuable to us to have like a time series database and Prometheus to do like the time series thing as well as the logging thing. Then more to our situation, defining the platform manifest was a good choice because we actually always know now what makes our application, right? All the components in our application, what was the latest version, and so on and so forth. So for our case, that was good. Then mixing and matching between component versions was also good. And then the only thing, and that's probably not applicable to you guys, and because it's a lot of effort, one thing that we wish now we should have done is we should have abstracted from container management, right? Because now, as you've seen, everything is on Mesos Marathon. Now we're going to move it over to another orchestrator, right? So we need to change all that type of stuff. It's doable, but I mean, for us, really, now we need to dedicate a bunch of resources onto moving it over to the new platform. And we could have just avoided that by making it really portable. So summary, I hope it was kind of like useful. So we're using a microservices approach. Perhaps with time to market, we're really able to ship updates to components in a very timely manner. As you've probably seen, it's not a free lunch. There's a nice blog post out there actually that talks about it, because you're entering a distributed system world. So it's a complex topic, right? You just need to be aware what you're dealing with. Tools and technology of choice requires governance, because if you follow like the microservices recommendations, every team can use what they want and things like that. If you don't have governance in place, you're creating anarchy. That's just a fact, right? Starts with diagnostics, it goes over data and so on and so forth. So if you have multiple teams building out an application like that, you need to have good governance in place. CICD pipeline automation are key, but again, we can only go to a certain point in our case. And then more on that topic, I actually started blogging out some microservices topics. I mean, it's been beaten to death, but a lot of that stuff is actually influenced from what we've built here on the Oracle blog. So with that, I think I'm right on time. I hope that was somewhat useful.